So today's module and presentation, we're going to be looking at combustion. So without further ado, by the end of this module, you should be able to show an understanding of the following areas. So the main constituents of complete and incomplete combustion. What's the requirement to achieve complete combustion? Visual signs of incomplete combustion. Causes of incomplete combustion. Identify burner flame pictures, and the ambient levels of CO and CO2 in atmosphere. So that's what we're going to be looking at throughout this presentation. So we're going to be going into a bit more detail with these things. So the first one we're going to look at is the combustion process and the basics of it. So for any combustion process, whether we're talking about natural gas or setting fire to a cardboard box, well, the cardboard box or the natural gas, they're our fuel. We need some fuel. We need oxygen. It's all around us. We use oxygen. We breathe oxygen in and we breathe out carbon dioxide, which we'll come on to when we look at the products of combustion. So we need oxygen. It's free. It's all around us. It's about 20% of the atmosphere. And then we need a source of ignition. So with gas, it's typically a pilot light or a spark. With a cardboard box, you're probably going to be using a lighter to set fire to a cardboard box. What's left over are the byproducts created by the product of combustion, are the products of combustion, or referred to as POC, products of combustion. So to illustrate this, we've got the combustion triangle. As I mentioned earlier, it doesn't matter what the fuel is, we need fuel. We also need the oxygen, because take away the oxygen and you wouldn't have combustion. That's the idea about fire blankets. If you've got a fire blanket and a fire occurs, you throw the fire blanket over and it starves it of oxygen. Fire extinguishers, a lot of the fire extinguishers, they remove the oxygen. The things like the CO2 fire extinguishers, the foam extinguishers, they remove the oxygen from the combustion process. So the flame just dies because it hasn't got any oxygen. And then we need that source of ignition. So it's all three things. So basically the triangle illustrates the three elements for a fire. We need fuel, oxygen, and that source of ignition. So we're going to look more in detail at that now. So one of the things about natural gas, we talk about relative density or specific gravity. If we think about air, air's all around us, that's got a specific gravity or relative density of 1. Anything below 1 is lighter than air, so it will rise. Anything heavier than air will fall. So natural gas, it's got a specific gravity of 0.56. That means it's just about half as heavy as air, so it's going to float. So for instance, if you walked into a room and the customer said they were smelling gas, it's going to be more at high level because the gas is going to rise up. So that's why they could be smelling it, because it's going up towards their face. Down at floor level, we might not have any indication and detect any gas. There are other gases we can come across apart from natural gas. We've got propane. If you do any caravanning or things like that, or you've got a gas barbecue, you've probably got one of those orange bottles, it's propane. Now that is actually heavier than air. It's about 1.5 times heavier, so that would fall. So basically, if you had a gas leak in a caravan, it's not going to be at high level, it's going to be at low level. Then there's a couple of other gases that we could come across. We've got butane, and that's used a lot for things like vehicles. So forklift trucks and things like that sometimes use butane. They're also used for your cigarette lighters and things like that. That's butane. That's twice as heavy as air, so it's even heavier than propane. So that's going to sit right down on the floor. And then going into the future, there's a lot of talk at the moment about renewable technologies and where gas lies. Well, as it is, we're using hydrogen. At the moment, we're blending it with natural gas. And we've got an 80% to 20%, so 80% natural gas, 20% hydrogen. The future is talking about going full-blown hydrogen. In fact, there are some properties up in the northeast which are running on full-blown hydrogen. Well, hydrogen is 0.0696, so it's about 7% the density of air, so it's really, really light. That's why it floats up. That's why historically in the past they used it for airships. They used to fill the airship full of hydrogen and it would float away because it was a lot lighter than air. The downside with hydrogen is a very flammable gas, and there were some incidents back then. So now balloons don't tend to be fueled with hydrogen. They don't have them in as their medium for lifting. They tend to use helium, which is a lot safer gas. But hydrogen is the future of the gas industry. That's what the people are saying we're going to be moving on to. That's why we've included it in here, because going forward, we're going to be looking towards hydrogen. So to get this stuff tonight, we talked about the fuel. So we've got these gases. We've talked about oxygen. It's all around us. But to get them to ignite, we need a flame temperature or an ignition temperature. Natural gas is about 700 degrees C. It's actually 704. Propane is 500, butane 503, and hydrogen is there at 535. So if we had a flame, which we measured at 500 degrees, it would light the propane, but it probably wouldn't light the natural gas because it's a lot hotter. It needs a lot hotter flame to ignite it. Then we look at this thing called calorific value. Calorific value is how much energy it releases for a volume. If you buy an energy drink now or anything, any food source, there's the labels on there. It tells you the fat content, it tells you the energy in there, and the energy is done in megajoules or kilojoules. And that's what it talks about. In gas, we now measure the energy of gas in kilojoules. And what we have is this thing called calorific value. How much energy we get from a cubic metre. Now back in the days, you can see on the presentation, we've got this thing called BTUs per cubic foot. We looked at gas meters in a previous presentation, and one of the gas meters was an imperial meter, and that used to measure gas in cubic feet. We now measure it in cubic meters, but we still sometimes, the old manufacturing instructions will refer to BTUs per cubic foot, so they're on there. So natural gas, for every cubic foot of natural gas, you'd get 1,034 BTUs. Now, with natural gas, we measure it in cubic meters, so a larger volume, and it's measured in megajoules, and we get roughly 38.76 megajoules per cubic meter. If we look at propane, you can see we're getting 93 megajoules per cubic meter, so a lot more heat for the same volume. We look at butane, that's even more. That's roughly 4 times the amount of heat from 1 cubic metre. Down to hydrogen, it's quite a small amount of heat from the cubic metre of hydrogen. So when and if we do go to full-blown hydrogen, we need a lot more of it to get the same amount of heat from it. But what we're going to concentrate going out throughout your journey on the MLP, the Managed Learning Programme, we're going to be talking about calorific value, and we're going to just refer to natural gas because that's the qualification you're looking for. It's the natural gas qualification. Now, natural gas, as we saw earlier when we talked about the makeup of natural gas, it's not just methane, it's made up of different gases that are all combined, and some of them are extracted and there's little bits of traces. So the calorific value depends on where it's made. We talked about in a previous presentation about the distribution, where do we get gas from? And I mentioned about Europe, I mentioned about gas tankers coming all the way from South America. So the calorific value can vary slightly. So what the distributors do, they mix the gas to give us the correct calorific value for the UK. So it's continually measured by the National Grid, and they'll publish the figures. So if you went onto a National Grid website and checked, they would tell you in your area what calorific value you would get. It's somewhere between 37.5 and 43 megajoules per cubic metre. In training and for assessments and things like that, we tend to stick to a figure, because if we changed it every week, we'd have to change documentation, we'd have to change presentations. It's just not viable. So we tend to refer to the one figure, 38.76 megajoules per cubic metre. So that's what we're going to be focusing on as we're going forward. So flame speed, how quickly does the flame burn? Okay, as you can see, there's a picture there of a candle with some, they're actually farrier's nails, what they put horseshoes on into horses. Why is that there? Because years and years ago, before we had clocks, that's how people could tell the speed. A thinner candle would burn quicker, and they worked out how long that time period would be. They put the nails in there, and as the flame burnt away, it got down to where the nail was. The candle would melt, the nail would drop onto the little tray, and it would signify that was like an alarm. That's telling somebody how long a period of time. So that's what flame speed is. Now obviously with gas you're lighting it and it's coming out through an injector, through a burner, and the different gases have different flame speeds. So let's have a look at these flame speeds. So if we look at natural gas, it's 0.36 meters per second. So roughly, if we looked at old-fashioned measurement, I'm an older guy, I remember feet and inches. It's about a foot a second. So every foot takes a second to burn. The reason we need to understand that is if we're lighting it and there's no pressure behind it, that flame, that it could go back into the pipework and disappear back down to the meter and cause an explosion. That's why we've got to make sure we turn things off. Flame speed on propane, 0.46. It's a bit quicker. Butane, 0.39, not far off the flame speed of natural gas. Now when we look at hydrogen, it's a lot quicker flame speed. So again with hydrogen, when we go forward to hydrogen, we've got to be aware of that. But we're going to concentrate mainly on natural gas now. So these percentages and ratios, so if we have a look at them, how much gas and air. So if we think about percentage gas and air, natural gas, methane that we talk about, the lower explosive limit, if we've got 5% gas in atmosphere, that's an explosive limit, and it's explosive up to 15%. So in the room I'm in at the moment, if I had somewhere between 5 to 15% of it was gas in the atmosphere, and I lit a match, I'm going to go bang. Propane, lower down the scale, we've got somewhere between 2 to 10%, the lower explosive limit to the upper explosive limit. Moving on to butane, that's between 1.8 and 9%. Hydrogen, it's a massive scale, anywhere from 4% to just over 75.5%. That's why there's concerns when we move to hydrogen. It's a more volatile gas. We're going to have to be a little bit more aware of that and treat it with a bit more respect. That's why there's a lot of research going into developing hydrogen for the use in domestic properties. We want it to be as safe as natural gas is today. So if we look at some basic chemistry, we have an atom, and an atom's a particle of matter that's uniquely defines a chemical element. So on there we've got hydrogen, it's coloured on green, carbon is a rusty colour, oxygen is blue, and nitrogen's like a mauve. So atoms form molecules. A molecule is the smallest part of a substance, and it's all the physical and chemical properties of the substance. And molecules are made up of more than one or more atoms. So when we looked at natural gas, we talked about CH4, 2 carbons, 4 hydrogens, if you cast your mind back to that presentation. And that's what it is, methane, natural gas, CH4. We talk about oxygen, O2, so we've got 2 oxygens there. Nitrogen the same, N2. Carbon dioxide, the same stuff that we breathe out, and one of the constituents of products of combustion is carbon and 2 oxygens. Water, H2O, 1 hydrogen, 2 waters. And then we've got carbon monoxide, the nasty stuff that it comes from incomplete combustion, which we're going to look at shortly. That's carbon, 1 oxygen. So just a little bit of basic chemistry to give you more of an understanding when we start looking at combustion. This is all about chemistry. So the process of combustion, it's this chemical reaction which uses that oxygen which is present and all around us. It's in the air. And then we've got the natural gas. So basically we put the CH4, the methane, we put oxygen to it, we get it from air. Now the nitrogen is about 8 parts so 80% of the air that we breathe is nitrogen. We don't use it, it's just an inert gas. It goes through the combustion process unaltered, so you don't tend to find in many of the textbooks they refer to the nitrogen. It's assumed because it starts off as nitrogen and ends up as nitrogen, we don't need to worry about it. Whereas the methane, the CH4, added to the 2 oxygen, the 2 lots of O2, what happens is we get CO2. So the carbon comes from the methane and helps to produce the carbon with 2 oxygens. So that's using 2 of those oxygens. The 4 hydrogens split and we have 2 hydrogens and 1 oxygen each. So that's why on the process of combustion we put in 1 volume of methane, and we need 2 volumes of oxygen for that to combust correctly. And the products of combustion, we end up with 1 volume of carbon dioxide and 2 volumes of water vapour. And that's complete combustion. It means that all the fuel has been used in the reaction, and therefore it's become this inert gas of carbon dioxide. So again, we've got that equation there. So it's important that both sides are equal, because this is complete combustion. We're using up the oxygen, we're using the methane. So there's only 1 carbon atom on each side, 4 hydrogen atoms on each side, the 4 oxygen atoms on each side, and it's balanced, it's equal. And that's complete combustion. So 1 volume of methane, the 2 volumes oxygen. It's a perfect mix. It's what's known as stoichiometric combustion. In the real world though, it's virtually impossible to achieve. The reason being is we always put more air in than necessary for combustion, because we don't want it tipping over where it's fuel rich and oxygen lean. And we'll come on to that as we start looking at incomplete combustion. So we've looked at the combustion process in terms of atoms and molecules, but as an installer we're not concerned about atoms and molecules, but there is this connection. That's why we need to understand it. So by using the combustion equation for methane, we can decide on the amount of oxygen we need for complete combustion. So if we look at that, 1 volume of methane, so let's say 1 cubic metre, which has gone through our gas meter, we'd need 2 cubic metres of oxygen. Now we'd need for that 10 cubic metres of air, because air, as I said earlier, is made up of 20% oxygen, 80% nitrogen. And what's going to happen, we're going to end up with 1 cubic metre of carbon dioxide, and then we're going to end up with 2 cubic metres of water vapour. So that's complete combustion. Air, as we've just said, is made up of round about 20% oxygen, 80% nitrogen. It's actually 21, but to make maths simple, we say 20%. So from now on, we're going to talk about 20% oxygen from air. That's what we're looking at. So that 2 cubic metres of oxygen for every 1 cubic metre, we would need 5 cubic metres of air for 1 cubic metre. So that's why we need 10 cubic metres for the 2 cubic metres. So where do we get that air from? It comes from all around us, but we need to get it into the house. We need to get it into the appliance. So we're going to look at ventilation in a later presentation. So there we go. We've got the 10 cubic metres of air, and from that all we're using is those 2 cubic metres of oxygen. And that's the process of combustion. 2 cubic metres of oxygen and the 8 cubic metres of nitrogen, which we don't need. So what we've got is 11 cubic metres in total. So that the fuel, the oxygen and the nitrogen not used. And coming out the other end, we should have 11 cubic metres of products of combustion. So we've ignited it, and then we've got the CO2, the water vapour, 1 cubic metre, 2 cubic metre, and as I said earlier, the nitrogen goes through totally unchanged, so it's not affecting the process of combustion. However, if we reduce the amount of air coming in, so reducing the oxygen level or the air level by 25%, what's going to happen is we're going to reduce the amount of oxygen we've got to use. So our 1 cubic metre of gas would only use 1.5 cubic metres of oxygen. So what's going to happen is we haven't got enough oxygen left over to give us complete combustion and carbon dioxide. This is where we get the carbon monoxide. So we'd get 0.5 cubic metre of carbon monoxide, and we still get the 2 cubic metres of water vapour. So this is the dangerous stuff. This is why we need to make sure we're getting enough air and enough oxygen into our appliances, into our boilers, our fires, our cookers, whatever our gas appliances are. So ventilation is really important, and the amount of oxygen that we get in to give us complete combustion. The carbon monoxide is a toxic gas, and it's a killer. People do die from carbon monoxide poisonings. That's why now, as best practice, we should be fitting carbon monoxide detectors. Wherever there's a gas appliance, we should have a carbon monoxide detector in that room, tested on a weekly basis by the customer, making sure that they're safe. If something happens, that's going to notify them that there's a problem, and that's where they get in touch with us as the experts for us to go out and we can test it and we can check it all out. So there's a lot of reasons where we get incomplete combustion. So we're going to look at some of those. Insufficient air, we're not getting enough air in. Now that might be we haven't got enough ventilation coming into the house. The customer's blocked up air vents because of drafts and things like that. It could be the appliance hasn't been serviced for a while, so it's got blocked up with fluff and dust into the appliance itself. It could be we're putting too much gas into the appliance. It's not being set up correctly. It might be we're not putting enough gas into it. So we've got too little gas, which is affecting that combustion process. It could be the flames are touching each other. It's what's called flame impingement, which causes chilling. The flame should be hot, but if they're touching, you get flame impingement and flame chilling, which can affect it. And then we've got what's called vitiation. Vitiation is contaminated oxygen. So one of the things that can happen is the products of combustion could be recirculating, and it could be down to where the appliance flue's being installed, it's not been installed correctly, and it's drawing back some of those products of combustion, and obviously they've got carbon dioxide in, not clean air, so that's getting drawn back into the appliance, and what's happening with that is that it's diluting the amount of oxygen in the air, so we're not getting the correct volume of oxygen. So let's have a look at each of these in more detail, just to give us a better understanding, and then we can look at how we would rectify this. So, insufficient air for combustion. It tends to be the main cause of incomplete combustion. This is the biggest cause that me and you guys will go out to if the appliance isn't burning correctly. The main cause is lack of servicing. 90% of customers forget how long it is between having appliances serviced. It's working well, they're getting up in the morning, the heating's on, they're turning the tap on, they've got hot water, they're putting the gas fire on, they're putting the gas cooker on, and they just forget to have them serviced. They don't do it maliciously, they just forget. But things start to get blocked up as it's drawing air in. Things can happen if it's drawing air out the room. We can get pet hairs drawn in, we can get dust, we can get fluff being drawn in, and that forms a substance called lint, and that starts to block up the air vents, so we're not getting enough air coming in. Also, it could be ventilation. If the appliance is in a room or in a compartment, the air grates get blocked up because the customer's trying to stop drafts. Overgassing and undergassing. Now, too much gas pushed into a burner with a fixed air inlet. So a fixed air inlet means it's just an opening, and the gas is coming through that opening, and that opening can't adjust. And if that starts to get blocked up with fluff and dust, it's reducing the size of the opening, so we're not getting, again, enough oxygen. Conversely, severe reducing gas pressure, there's not enough suction. As the gas goes through what's called an injector, and we're going to look at these things as we're going forward on further presentations and further slides and things that we do. The gas goes through an injector, and in going through there, it starts to drag the air in with it. Now, if there's not enough pressure, it doesn't drag enough air in, so again, we don't get that nice air-gas mixture. So it's for those reasons it's essential that appliances are set up and the pressures are set correctly. So the flame impingement, I talked a little bit about it. What happens is appliances can have one burner, or they can have multiple burners that are stacked together. Now, if the burners are correct, the flames are coming up, but if they're not put in properly, the flames can touch each other and impinge, and then when they're touching, you get a cold spot, and that can cause sooting. Carbon is if you got carbon and compressed it for long enough and hard enough, you get a diamond. We can't do it for that long, but what happens, it's the black sooty remnants that are left. As the flames are touching, we're getting incomplete combustion, and one of the products of that is this black sooty carbon, the soot that formed on old coal fires and things like that. So we can get the soot form, we can get rust and debris going onto the burner, so it restricts the amount of gas and air coming through, so it affects the way that it's burning. Then we've got, in turn, if it's hitting a cold surface where the flame shouldn't be hitting, again we're going to get that same thing. We're getting flame chilling, which is what's going to cause problems if it's below that ignition temperature. Natural gas, we talked about 704 degrees. If it's below there, what's going to happen is we're going to get incomplete combustion. Other causes of flame chilling, if we've got fan assisted burners, on a lot of modern appliances there's a fan that draws the air in and pushes the products of combustion out. So if the air gas ratio valve isn't set up correctly, we've got too much throughput through it, that can cause it. Not set correctly, the flame picture isn't correct. So there's all sorts of things which can cause this incomplete combustion and flame chilling. That's why it's really important when we're going out and checking appliances, we're setting them up correctly. And we're going to cover all that throughout the course. We're going to look at appliances and all this type of thing, and we're going to cover it as part of the MLP process. And then there's the vitiation, reducing the level of oxygen that's been drawn in there. And for instance, an open flued appliance, an older appliance which is open flue, so a gas fire in a chimney, that's what's called open flue. The flue goes up outside, it takes this air for combustion out the room. Now what we could get is spillage of products combustion. That means the flue's got blocked. So what's happened could be Mr. Crow's decided to build a nest up on the chimney stack. Nobody knows it's there. So the products of combustion can't go out through the chimney. So they come back and go through the appliance. That's called spillage of products of combustion. And then it's coming back in. It could be that it's a balance flue where you've got an air inlet on the outside of a flue duct, and there's a crack in there, it's become damaged, it's corroded, and you're getting reverse circulation, so it's drawing some of the products back into that appliance, so we're not getting this clean, fresh air that we need. So in both cases, you're going to get the same result. Recycling back off the burner, we're going to get insufficient oxygen, and what's going to happen, the CO2 levels are going to alter. So somewhere between 1.5% to 2% of the room volume can reduce that level enough to affect the combustion process. So here's some of the causes of incomplete combustion and the actions and remedies. So things like incomplete combustion by blockage of air grills and vents on open flued appliances. The solution to that one is, if somebody's blocked an air vent, explain to them the air vent shouldn't be blocked and it needs to have the blockage removed, because if that's blocked, we're not getting the right amount of oxygen in there. Now it could be blocked because it's drawn fluff and dust in, it just wants a good clean out with a brush and a hoover, so we can clean that out. Incomplete combustion by blockage of the primary air ports. So on some of the appliances we've got primary air ports, and again we're going to discuss these things more in detail when we look at types of burners. So it's drawn in air and it's drawn in fluff and dust out in with that. And again, we need to clean that out, and it's part of a service on an appliances. We clean these things and we check them. Incomplete because of blockages in heat exchangers. Appliances haven't been serviced for a long time. So what happens is you start to get a yellow tipping on a flame, and eventually it gets worse and worse, and it starts producing the bright yellow sooty flame. A little bit like if you got a candle and put a saucer over the top of it, you'd end up with a black mark on it. That's the same thing. That's the carbon that's produced from combustion. So again, we'd remove the blockages, we'd clean it out, we'd give it a good service. Incomplete combustion caused by overgassing. We check the burner pressure. We always, on a service, check the pressures going into boilers and fires and cookers. Now there are things called burner pressures and working pressures. We're going to look at those again as we're going further into the course. But this is something that we check, and we'd always refer to manufacturer instructions. It's important that we set them up correctly, not just as a rule of thumb, not by what my mates told me I should set to that, but always do it by manufacturer instructions, because they're the people that made the appliance. They know what pressure is the most efficient pressure for it to work correctly. Overgassing, again, excessive gas rate. What could have happened is the injector, the little nozzle where the gas comes through, somebody could have tried cleaning it out, but they've cleaned it out by poking something in there. They've opened the hole up, so it's letting more gas in than it was designed to do. And what happens with that? Again, we're getting too much gas, it can't draw sufficient air in, so we're getting incomplete combustion. The pressure's okay, but the volume of gas coming through because the injector's increased. So if we're getting that and we've checked the pressure, then we'd inspect the injector to make sure the injector's correct. This flame impingement, looking at flame pictures. If we've taken an appliance or stripped an appliance down with multiple single burners and we're putting them back in, making sure they're in line, they're not impinging, they're not touching each other, checking the alignment and things like that. And then the other one, particularly with cookers and things like that. We get a lot of imported cookers and hobs into the UK. Now a lot of them come dual fuel ready, so they can go on natural gas, or they could be fitted in a caravan on propane, on LPG, liquid petroleum gas. So they come with a separate set of injectors, because as we saw earlier on, liquid petroleum gas has got a different specific gravity and it's got a different calorific value, so we don't need as much propane as we do natural gas. So it has a smaller opening in the injector. So if it's got the wrong injectors in there, that can affect it. So if you got called out to a caravan, if you're working in caravans and the flame's too small, it could be it's got a set of natural gas injectors on there. On the reverse of that, you get called to a domestic property. The customer's just had a new cooker and they complain the flames are too high, they're bright yellow, it's sooting the bottom of the pans up. It could still have the LPG injectors fitted. So those are things to watch out for, which talk about incomplete combustion. So visual signs of it, if we look at appliances, so if we look at this first one, that's an older boiler, it's on the wall, and if we look around the appliance and on the top, there's some stain in there. Now that could just be, it's an old appliance and it's just heat. Heat rises, heat draws dust in, it might not be anything at all, but to an experienced gas engineer like myself, I'd look at that and the first thing I'd think of is, that could be a sign of incomplete combustion. I need to check that out. I need to inspect it and check the seals on that appliance to make sure there's no products of combustion coming out. Make sure the appliance is burning correctly. Because it could be burning correctly, but if the case seal isn't correct, we could have some products of combustion. Instead of going through the flue, they could be being released into the room or area where that appliance is located. If we look at that gas fire, that's a real bad example of a gas fire that's not been serviced properly. We can see it's scorched on the front canopy. That's the bit of the front. We can see where the paint's worn off. It's really in bad condition. If I saw that, the first thing I'd be doing is saying to the customer, look, you can't use that appliance. I'm going to condemn it. I'm cutting that off. It's an absolute danger. But not all appliances that are burning incompletely and incorrectly are that noticeable. Some of them look quite okay. It's when you start getting in and inspecting them and checking them. And then things like these, what we call live fuel effect fires, gas fires that are designed to look like a coal fire. They've got coals or log effects on there where the flame passes through there to give the illusion of a true open fire. But if the coals or the logs aren't set up correctly, what we're getting is what's this flame impingement. So the flame's coming up and it's hitting the bottom of a coal or a log instead of coming at the side of it. And we're getting this flame reversal, so we're getting the black carbon, the soot deposits. So that again, that just might want a good service, a good clean out, and the coals or the logs setting as per the manufacturer instructions. So if you're going to work on things like this, it's really important you have the manufacturer instructions to look at the pattern of where the coals or the logs fit. That's a fire there. That's what's called a duplex burner. It's actually 4 flames or 4 burners. The middle 2 light independent of the outer 2. And the middle 2 are burning reasonably well, quite a decent blue flame, but the outer 2, so that's where the injector, the air port, has been drawing some dust or fluffing, or somebody's cleaned the injector out and they've enlarged it, so it can't get enough oxygen in for the volume of gas that it's burning. So again, that's not burning correctly. That would trigger me to say, look, that appliance needs checking, probably needs a good service on that one. These two, we've got a cooker burner there, and then we've got a boiler, both bright yellow tips, classic signs of incomplete combustion, not enough oxygen in there to sustain combustion, and all that probably needs, both those appliances, a good clean out. Just stripping down, clean any fluff or dust out, put them back together, relight them, check the pressures, and those appliances are probably good for a few more years. So, carbon monoxide, the dangerous stuff. In reality, unless we lived on a desert island, you're going to come across carbon monoxide. It's produced by all the carbon fuels we talked about when we were extracting gas and oil and things like that. If you burn any carbon fuel, fossil fuel, so solid, so coal, oil, any of the gases, we're going to get products of combustion and we're going to have carbon in there. So we hope we're going to get carbon dioxide coming out, but if we don't, we get carbon monoxide. So inside a property, we could get 9 parts per million just in atmosphere. Quite normal, quite natural. We measure carbon monoxide in ppm, parts per million. We tend to measure carbon dioxide as a percentage or parts per 100. So in a house, we could get up to 18 parts per million with a gas cooker running. So Sunday lunch, somebody's doing a meal, they've got the gas cooker on, it's going to be producing some carbon monoxide. But it's quite safe. It's not going to kill us or cause us any harm at 18 parts per million. We could, with a wood burning stove that some people have, go up to 30 parts per million. Oil heaters, 7 parts per million. But looking at other things that we could get them, if we're sat in our car, stuck on the track, stuck on a motorway, we're trying to get somewhere, there's a traffic jam, we could have anywhere between 9 and 25 parts per million. If we drove into an underground car park, 44 parts per million, that's fine because it's short-term exposure to low levels. There's 2 ways that carbon monoxide can cause you harm. One is long-term exposure to low levels. So for instance, a gas appliance, let's say for a gas fire, it's producing carbon monoxide and the customer's sitting in front of it on a winter's day for 3 or 4 hours a day. That carbon monoxide's going into their body and it's sticking to the blood and it's stopping them getting the oxygen into the blood. And that could take weeks before they start to feel any effects from it. The other one is short-term exposure to high level. So the gas fire where the crows built the nest on the top of it, excuse me, we're going to get high levels of carbon monoxide. Potentially, if it's so high, 2 or 3 minutes in that room, and we could start feeling the effects. And the effects, depending on the level, as we'll see later on, could start off at feeling a little bit poorly, resulting in fitting and ultimately death. So, carbon monoxide, totally odourless and colourless. Excuse me. That's the result of incomplete combustion. And it's formed when a carbon atom and an oxygen atom form that carbon monoxide molecule. And it's typically when the fuel-air ratio is fuel rich, with too much fuel, not enough oxygen. And it's toxic and it gets absorbed into your blood. And what it does, it's like oxygen starvation. You're not getting enough oxygen into your blood. So one of the symptoms is yawning. Oh dear, your body's trying to compensate for the lack of oxygen by you yawning and dragging air in there. 4,000 parts per million in air could cause death within a few minutes. So obviously we've got to be aware of these things and we've got to make sure appliances are burning correctly. So if we look at this, we've got the percentage CO, we've got the parts per million, then we've got the saturation in blood, so how much percentage is in our blood and what the symptoms are. So starting at the beginning, 100 parts per million. And all these are affected by different things. The age of somebody, the older somebody is, the longer the lungs have been working. Younger babies, things like that, the lungs aren't quite developed. Larger people, they've got more fat. Fat absorbs carbon monoxide, so I'm lucky I absorb carbon monoxide compared to somebody who's thin. And obviously people with health issues, somebody who's got breathing difficulties, anybody that suffers from things like bronchitis, emphysema, anybody that's suffering from long COVID, where they've had breathing difficulties, they're not getting the volume of oxygen in because the lungs are affected. So they're going to be more likely to be affected by carbon monoxide than somebody who's got healthy lungs and things like that. So looking at the chart there, 0.01% or 100 parts per million, that's going to equate roughly to 13% CO2 in the bloodstream. You're going to get a slight headache within 2 or 3 hours. So if you're in a room with an appliance producing that for 10 minutes, you're probably not going to feel any effect. But if you're spending 15, 20 minutes in there every day, eventually over a period of time, that's going to build up. As we start increasing it, we're talking about 200 parts per million, 20 to 30% mild headache, dizziness, sickness, starting feeling tired after 2 or 3 hours. 400 parts per million, 36% headaches, starting at the front of your head, starting feeling sick within 1 or 2 hours, starts to become a danger to life within 3 hours. 800 parts per million, 50% saturation in your blood, because as I say, it stops your blood picking up the oxygen from your lungs and going around your body. Severe headaches, starting to get dizziness, convulsions within 45 minutes, unconsciousness, possibly fatal in 2 to 3 hours. Now we're getting into the realms of we don't really want to be anywhere in these situations. 1,600 parts per million, 68% saturation. We're talking about headaches, dizziness, sickness within 20 minutes, unconscious with fatal consequences in 2 to 3 hours. Really serious stuff. Even more, 3,200 parts per million, 70 to 75% saturation, headaches, dizziness, sickness within 10 to 15 minutes, unconsciousness with fatal results, quarter of an hour, 15 minutes. 6,400 parts per million, 80% saturation, headaches, dizziness, sickness, 1 or 2 minutes, very short period of time, unconscious, fatal results, 15 minutes. And the last one, 12,800, 85 to 90% saturation, immediate medical symptoms. If you walked into a room with that saturation in there, you might not smell the CO, but you're going to be affected literally straight away, fatal within 1 to 3 minutes. So that's why it's really important that we do our job properly to protect our customers and make sure all this could be stopped if they've got a CO alarm. So it's always worth mentioning, if a customer hasn't got a CO alarm, advise them, have a CO alarm fitted in the room where that appliance is. That'll protect them from any of this. So we've just covered combustion, so hopefully you've got a better understanding of combustion, natural gas, combustion and incomplete combustion. It's really important that we can identify incomplete combustion, so that's something to concentrate on, looking for identifiers. What I do, if I go to a friend or a neighbour, have a quick look round, see if they've got something, you might just save their life. So that's combustion. Until the next presentation, thanks very much for watching. I'll see you soon.